Hello everyone, and welcome to our lecture on z-scores and z-tests. In this video, we'll be discussing, you guessed it, z-scores and z-tests. In our last video, we saw that statistics help us to decide whether or not samples that we collected came from the null population. Now, it's time to start answering questions using statistics. But first, I want to take a minor detour to talk about interpreting scores in a distribution. The key idea here is that you always need to interpret means along with their associated standard deviation. The smaller the standard deviation, the better the mean captures the data as a whole. In a normal distribution, about 68% of the data is located within one standard deviation of the mean. 95% of the data is located within two standard deviations of the mean, and about 99% of the data is located within three standard deviations. Let's see an illustration of this. So here we have a normal distribution. Notice that the mean of this distribution is mu, and then on our x-axis we have differences from the mean represented in terms of standard deviations. Here, because we're dealing with populations, of course both the mean and the standard deviation are represented in Greek letters, mu for the mean and sigma for the standard deviation. So let's say that our population mean here is 100. If we look at this red zone here, the zone that is within plus or minus one standard deviation of the mean, we know that 68% of our data is going to fall within this band. Next, if we look at all of the data within two standard deviations of the mean, so that's the red zone plus the blue zone, this area is going to contain 95% of the data. And again, that's 95% of the data falling within two standard deviations of the mean. If we go even further, over 99% of the data is going to fall within three standard deviations of the mean. So that's the red zone plus the blue zone plus the green zone. Now, let's say that our population standard deviation is 10. In combination with our population mean of 100, we now know that 68% of the data is going to fall between scores of 90 and 100. We also know that 95% of the data is going to fall between scores of 80 and 120. Now let's say that our standard deviation instead is 30. If this is the case, then 68% of the data would fall between the scores of 70 and 130, and 95% of the data would fall between the scores of 80 and 160. The key point here is that the smaller our standard deviation is, the smaller the range of scores is that contains each chunk of the data. So, again, when the standard deviation is 10 as opposed to 30, 95% of the data falls between scores of 90 and 110, a difference of only 20 points, as opposed to falling within the range of 70 to 130, a range of 60 points. So, it's easy to compare scores within a distribution. Let's say we have a distribution with a mean of 100 and a standard deviation of 10. In this case, a score of 120 is above average, a score of 90 is below average, and of course, a score of 120 is better than a score of 90. But what if we wanted to compare a score in this distribution to a score in a different distribution, say with the same mean, but a standard deviation of 30, sort of like the example we saw on the last slide? Would a score of 120 be equally impressive in both distributions? Let's look at a more concrete example. Let's say we want to compare how student X did in my 10B course last year, compared to how student Y, one of you guys, is doing in my 10B course this year. So let's say that last year's 10B class had a mean of 72 with a standard deviation of 5, and that student X's score was 80. And let's imagine that this year's 10B class has a mean of 76 with a standard deviation of 8, and that student Y's score is 80. So the question is, did students X and Y do equally well in comparison to their classmates? To answer this question, we can convert their raw scores into z-scores. Z-scores are a standardized score that take both the mean and the standard deviation of the sample into account. Let's talk about this in a little bit more detail. A standardized score converts all scores into the same metric, and what this means is that all z-scores can be compared to each other regardless of where they came from. Z-scores tell us how far away a score is from the mean in terms of standard deviations. And the formula looks like this. So in the numerator, the top of the fraction, we have the difference between a given score, represented by x, and the mean, represented, of course, by mu. In the denominator, on the bottom, we have the standard deviation. In other words, the typical difference between a score and the mean. By dividing the difference between each score and the mean by the standard deviation, we get a z-score. So let's see this in action. So again, this is just copy and pasted from the last slide. We have information about student X and student Y. They both got the same score of 80, but the mean and standard deviation of the samples are different. So let's start by finding the z-score for student X. We subtract the mean of the sample that they were drawn from, 72, from their score, 80, and then divide that by the standard deviation, which is 5. So 8 over 5 gives us 1.6, meaning that the z-score for student X's score is 1.6. Same thing for student Y. We subtract the mean of the sample that student Y came from, 76, from their score of 80, and divide that by the standard deviation of the sample that they came from, which in this case was 8. So we end up with 4 divided by 8, which of course gives us a z-score of 0.5. So who did better? Thanks to the z-scores, we can see that student X was farther away from the mean, farther above the mean, so they did better relative to their classmates than student Y did, simply because a z-score of 1.6 is higher than a z-score of 0.5. Let's talk a little bit about some useful properties of z-scores. We can convert all scores in a distribution into z-scores. A z-score distribution will always have a mean of 0 and a standard deviation of 1, by definition. Furthermore, if the original distribution was normal and randomly selected, then the z-distribution that we create by converting all of the scores into z-scores is called the standard normal distribution. Importantly, z-score distributions keep the shape of their original distribution. So if our original distribution was normal, then the z-score distribution will be as well. But if the original distribution was skewed or bimodal, then our z-score distribution will be as well. So z-scores tell us how far away a score is from the mean, how extreme it is, and let us compare scores across distributions. We can also look up probabilities associated with z-scores, in other words, the likelihood of obtaining particular scores. And this leads us to one main use of z-scores, which is that we can use them to answer statistical questions. For example, does a sample come from the population that it's being compared to? So let's look at a concrete example. Let's say we want to know if the IQ scores of Sci 10B students differ from those of everyone else who's taken an IQ test. In other words, are they drawn from the same population or from a different population? Now, IQ is a very complex and very fraught topic. So why use it in this example? Well, z-tests can only be run when we know population parameters. That is to say, the population mean, mu, and the population standard deviation, sigma. Conveniently, for IQ scores, by definition, the population mean is 100 and the standard deviation is 15. So we have all the information that we need in order to run a z-test. Let's go ahead and conduct null hypothesis significance testing, practicing what we learned in the last lecture. So, our research question is, are the IQ scores of Sci 10B students different from those of everyone else who's taken an IQ test? We'll start by stating our null hypothesis, represented by H0. Our null hypothesis will be that the IQ scores of Psych 10B students are not different from the IQ scores of everyone else. As always, the null hypothesis is that there is no difference. Our null hypothesis is that mu is equal to 100. In other words, that it's equal to the mean of the null population. Our alternative hypothesis is that the IQ scores of Psych 10B students are different from the IQ scores of everyone else. And we can express that by saying that mu is not equal to 100. So, a question for you guys. Based on these hypotheses, are we running a one-tailed or a two-tailed test? And the answer is that this is going to be a two-tailed test. We can tell because our null and alternative hypotheses are non-directional. There's no discussion of whether IQ scores are higher or lower, we're just interested in whether they're the same or different. Let's move on to step 2 of null hypothesis significance testing. We need to set our alpha value, so we can ask ourselves, are we okay with a 5% chance of being wrong? As I mentioned in the last video, an alpha of 0.05 is a widely accepted rule of thumb in psychology. And if it's good enough for psychologists in general, it's good enough for us. So we'll pick an alpha level of 0.05. Now we can ask, what's our critical value? We can find our critical value by consulting the unit normal table. You can find this whole thing as a PDF on GouchoSpace. I'll show you some relevant parts in these slides. So the unit normal table will look something like this. You'll see some illustrations at the top of normal curves. Notice that we have a vertical line representing a given z-score, and the normal curve itself is divided into two areas. The shaded area, known as the body, represented by column C in the table, and the tail, the unshaded region, represented by column C in the table. So, for any z value, this table gives us the proportion of the normal distribution that's in the body, in other words, that lies below the given z-score, the proportion that lies in the tail, that is, that lies above the given z-score, and the proportion of the distribution that falls between the mean, the center of the distribution, and our z-score. So which proportion do we want to look for? Remember that alpha is a proportion of the null population, and specifically that if a sample mean falls into the area marked off by the alpha, there's a strong chance that it came from another population. So as it turns out, column C, the proportion in the tail, marks off a region as well. So we'll treat that as our alpha. If we find our alpha value in the table, we can find the z-score associated with it. The z-score marks where the alpha region begins. It's our critical value. And if our calculated z-score is greater than this critical z-score, we'll be able to reject the null. So looking at this illustration here, effectively the non-shaded region, C, is going to be our critical region. So we want to find the critical value for an alpha level of 0.05 and a two-tailed test. So what proportion should we look for? It would be logical to look for 0.05, but this is actually incorrect. And the reason is that we're running a two-tailed test. Recall from the last lecture, this means the 0.05, the 5% of the alpha value, gets split in half in the top and half in the bottom of the distribution. So we want to look for 0.05 divided by 2 in the proportion for the tail region. So we look up the z-score associated with 0.025 and find that it's 1.96. Thus, our critical value is 1.96, and if our calculated z-score is greater than 1.96, it will be significant. It will be unlikely that it happened due to chance. Now we can move on to step 3 and actually calculate that test statistic. Remember that our population parameters, we have the population mean of 100 and the population standard deviation of 15. Let's say for this example that our sample mean is 105 and that our sample size is 75. So let's go ahead and calculate our z-score for this sample. When we're calculating the z-score for a z-test, the equation is slightly different. The numerator, the top of the equation, is our sample mean minus our population mean, and we divide that by the standard error, in other words, the standard deviation of the sampling distribution. You can watch the StatsClass video for more information on calculating z-tests. So, what is sigma sub m? This is the standard error. In other words, the average distance between a sample mean and the population mean. We can find the standard error by dividing the population standard deviation by the square root of our sample size. Once we've figured out the standard error, we can then use the z-score to calculate the distance between the sample mean and the null population mean, controlling for the average distance between the sample means of that null population and the null population's mean. So, we'll begin by calculating our standard error, which again is the standard deviation of the population divided by the square root of the sample size. Plugging in the values that we have, our population standard deviation is 15, and again we know this because, by definition, IQ scores in a population have a standard deviation of 15. and we divide this by the square root of our sample size, which is given as 75. This gives us a standard error of 1.73. Then, we can plug that into our equation for the z-test. In the numerator, we subtract the population mean, which again by definition is 100, from our sample mean, which is 105, and then divide that by the standard error. So we end up with 5 divided by 1.73, which works out to 2.89. This will be our test statistic. Now, for step 4 of null hypothesis significance testing, we make a decision. We can make this decision either by comparing p and alpha values, or by comparing the test statistic to the critical value. In this case, we've figured out our critical value and our test statistic, so let's go ahead and use those. So what's our decision? Well, our test statistic, 2.89, is greater than the critical value that we identified of 1.96, so we reject the null, and conclude that Psych 10b students' IQ scores are significantly different, in this case significantly higher, than IQ scores in the general population. Which makes sense, you guys are a clever bunch. So what if we wanted to find the p-value for our test statistic? Remember that the p-value is the probability of a test statistic being equal to or greater than the observed statistic if the null hypothesis is true. So if we find the test statistic in the z-score column, the p-value will be in column C for the proportion in the tail. So if we scroll way down in our table of z-values, we'll find, as we see in the bottom row, that a z-score of 2.89 corresponds to a p-value of 0.0019. In other words, there's a 0.19 chance of finding a statistic this high or higher if we're sampling from the null population. Because 0.0019 is less than our alpha of 0.05, we can reject the null. So, a key thing to remember here is that we only need to compare p to the alpha or compare the test statistic to the critical value. One of these comparisons is enough to test our hypothesis and reach a conclusion.